Again, what's being recorded is just what I'm sharing on the screen, no personal information. If you speak up, it won't even show up. Oh, that's funny. So you won't hear the question, so I'll have to repeat the question. So if you have a question, chat is fine. I have the chat pulled up on a separate window. You can speak out, and I'll just say the question out loud so that it's recorded. Nothing about you will be recorded here. All right. Continuing on, types of graphs, box plots, histograms. Those are the main types of graphs for the quantitative data. In qualitative data, we have bar graphs and pie charts primarily, but there's lots of others, but these are the types in the course. Studies. There's types of studies as well. Observational study, you're just taking a look. You're not actually doing any physical changes to what you're observing, or as little as possible. Experimental studies, you're actually doing a treatment, whether that treatment is blood changing, like giving someone testosterone to see what the effect is, or giving them something to listen to see what the effect is. You're not just looking at them. Now, there are some things that some people think are experimental, but they're actually observational. For example, if you wanted to know how healthy the fish are in Utah Lake, then you actually need to catch them and pull blood to see if they have high levels of mercury or whatever else. That's not an experiment. You're just pulling the blood out of them so that you can observe what's in the blood. Now, if you put something new in them, now it's an experiment. So it's not necessarily hands-off for observational. Okay. Confounding is when you're trying to do an experiment on something and there's other things going on that you didn't account for or that you couldn't remove. One example is weight loss. It's like, hey, I gave someone this drug and they lost a bunch of weight, but what they don't tell you is you also paid them to go to the gym to make your drug look better. So that's a confounding variable. Yeah, they lost weight, but why did they? I don't know. Was it because of the drug you gave them, or was it because of that they went to the gym? You try to create your experiments to decrease the number of confounding variables. So that's why it's called a controlled experiment. You're trying to control so there's only one change. Genetics is a confounding variable in a lot of cases. And so a lot of studies have been done with identical twins to decrease that confounding variable. Control treatment groups. So this is the group that's being experimented on, the treatment group. And the control group is the one that's not being experimented on. Sometimes the control group is a placebo control group. So they think they're being experimented on because they're getting a pill just like the treatment group is, but that pill's a sugar pill. And hopefully you're not looking at the effects on like blood sugar level, because then a sugar pill is going to be a treatment, not a placebo. The placebo effect, they used to think that this was just made up, but it's actually the body, your belief in something, having the body create the chemicals. Your body's, if any women that have gone through childbirth naturally, you know your body has the ability to create whatever painkillers you need in the moment to make it so that you live through that. Same thing with testosterone. I mean, we have men, when it's time, when you need it, when you're a toddler or a teen, the body makes it. And when you don't need it anymore, the body stops making it, which is sad because we live longer than we used to. We still need it, but evolutionarily, we don't make it as much anymore. I'm speaking from experience. Okay, so blinding. Single blinding is when the participant in the study doesn't know if they're in the treatment or placebo group. It's pretty hard to single blind if you're in the control group and it's not placebo. Like, okay, so I want you guys to stand up and do squats, and I want you guys to sit in the chair and not do squats because we want to see how much squats affect blood pressure. Well, you know which one you're in. So it's really the placebo groups that have the blinding as a potential. Double blinding, somebody knows, but the people giving the treatment or the placebo don't know who's who, and the people getting the treatment or placebo don't know what they're getting. So double blinding is really what you want to do. Okay. An example, clinical trials of a weight loss drug containing Garcinia cambogia. The subjects were randomly divided into two groups. Okay, the first received an inert pill along with an exercise and diet plan. The second received the test medicine along with the same exercise and diet plan. So this time they were both told to eat and exercise the same way. So that minimizes that confounding variable set. One got an inert pill, that's the placebo, and one got the test medicine. So the control group would be the inert, inert pill group. The treatment is the test medicine group. Ah, my goodness. Now, patients do not know which group they are in, nor do the fitness and nutrition advisors. So both sets of people don't know. This is double blind. So an example of neither would be the effects of smoking on birth defects. You have people that are clearly not smoking and people that are clearly are smoking. There's no way to give them a fake cigarette that they know. So there's no way to do any kind of blinding in that case. That would be an example. Now, the reason why double blind is better than single blind is if you really believe in the medicine you're giving and you're trying to show, you might have body language when you give them the placebo. And they might be like, oh no, this is the sugar pill, it's not going to work. Well, so much for your placebo effect, because now your body's going to be like, oh, this is not going to work, I can take the day off. Great. So double blind really is the way to go. There's also called a crossover. Halfway through the study, you switch the placebo and treatment groups without telling anyone. And then you can take a look at if the medicine really is working, if all of a sudden the other group has the benefits, whereas the first group didn't. Or if you happen to be given bad medicine, all of a sudden the other group starts to die. Got to be careful with this stuff. Is this best described as an experiment, a controlled experiment, or a placebo-controlled experiment? So an experiment would be smoking on birth defects. No, most people, sorry, that's the controlled experiment, because you'll have to have a group that's not smoking and a group that is smoking that are pregnant, and you could look at birth defects afterwards. This one's a placebo-controlled experiment. Just an experiment is what most people do for their New Year's resolutions. Like, I'm going to stop eating sugar. And there's no way for them to look back and go, what if I had kept eating sugar? Or most people don't stop, and then a year later they're like, what would have been possible if I'd actually kept that resolution? So they don't stay in the treatment group long enough, and they don't have a control group to compare with, or they stop doing the treatment group and they turn into the control group, and then now there's no two groups. So it's just one group, and you can't really tell what's going on. All right, this section, let's just keep moving. Describing categorical data graphically. So, frequency table. In this case, just showing, this is examining police reports for 210 recent total loss collisions. Determine if color has something to do with accidents, color of cars. So there were 21 blue cars that were in total accident, total loss collisions. And it says 10%. Now what this is all about, let's see how big this calculator is. It's going to fit on the recording. So this problem has 210 total. So 21 divided by 210 is 0.1. Now the relative frequency can be written in decimal, and that's common. And that's in the Magnets and Payne project, for example. There was not the percentage given, it was just the decimals given. Or you can write it in percent form. Those are both common, but pick one and stick with it. So 42, well, that's twice as much as 21. So we expect 20%, but again, you work it out. 42 divided by the total. 0.2, which is 20%. So 35, 30, etc., you're just dividing by the total and simplifying. So this is how you work out the relative frequencies. You take the frequency count and you divide by the total in the count. To go backwards, if we have 19%, if you happen to know, here, let me clear that. 19%, by the way, especially on a test, if you just don't want to take chances with moving the decimal place the right way, just divide by 100. If it's a percent, 19%, percent literally means divide 100, percent. So we got that number, we multiply that by the 210, and that's 39.9. I'm assuming that's 40, but here we have a question, is it 39 or 40? Very close to 40. 20% was 42. So you can go back and forth. If you have the total, you can go back and forth between frequency, which is just the count of how many, and relative frequency. The relative frequency, or the frequency, you can create histograms for. Okay, now bar chart. In this case, we have qualitative data, the color of the cars, and the frequency is how many there are. So there is some math involved, some numbers involved. There are some numbers with qualitative graphs, but they're also based on qualitative data. The thing about this, like the gaps in between, you could rearrange these in any way you wanted, and it wouldn't change the data. You would still see that the green and red are the highest bars, no matter what order you put them in. And there typically is a gap between, because there's no natural ordering of these, because they're not numbers. You might like alphabetical, but that's not any better than reverse alphabetical. Okay. Now, bar chart gaps are meaningless. Yes. Use the charts above to answer the following questions. What number of cars were white or black? So we look up the white, 35 cars. Black, 30 cars. Black or white, 30 plus 35. There were 65 cars that were either black or white. What percent of cars were not blue? Well, we have percent of cars, blue, 10%. So 10% were blue. That means 100 minus 10, 90% were not blue. This is the complement rule. This is in normal distribution as well as probability. 1 minus some 100% minus a percent is how many that are not that. That's a lot easier than counting up the other bars. You could also count up 20 plus 20 plus, what is that? 17 plus 19 plus 14, and add all those up, and it should be 90. But that's a lot harder to do. Pie chart is another way. Pie charts are cool because they're nice and colorful. However, if you don't have color printer, then they're not very cool. And also, if you do have a color printer, it costs a lot more to make these. So when we were doing more paper presentations 20 years ago, bar charts were much more common than pie charts because of the how much more money it costs to create pie chart paper stuff. But now when we're back to online media, then colors are back and pretty pictures, so now pie charts are more common than bar charts. Would you rather be given the police data as a frequency table, a relative frequency table, or a bar chart, or a pie chart? If I were the police car, if I were the head of the police department in New York City, the pie chart's fine. I think I would prefer the percent of cars. Because the number of cars, 41 cars. No, that's not New York numbers. That's smaller town numbers. So I would want a percent so I can apply the percent to the numbers of cars on my roads in New York. And the bar charts are a little bit easier to compare. Whereas in the pie chart, if I don't have that 19% and that 20%, if that weren't there, it'd be really hard to tell which of these are bigger. With the bar chart, you can see which one's taller. So I would prefer the bar chart, even though the pie chart is, you can make a better presentation and get people excited about it better, perhaps. Because maybe that depends on your presentation skills. All right, so here we have an example. Jasmine, her spending, rent, food, fun, and other. Use the chart below to determine what percent of her total spending she spent on rent. So the percent total is going to be how much on rent over how much total times 100%. That would be our basic thing that we have to work out. And we don't have how much total, but we can find it. So we add up the individual categories. $1,600. And now we can figure out how much she spent on rent, $444. $27.75%. It says round to the nearest whole percent. Now this is important. When you have instructions that say round and also have the word percent in there, you must go to percent first and then round. Because if you round to the nearest whole percent and you start with a 0.2775, you're like, round to the nearest whole number, that's 0. And then you might say 0%. So you've got to go to percent first and then round. 28% would be the approximate whole percent. Yeah, $444. She's still living with her parents. Okay. Quantitative data. Here we have an instructor that gave a quiz to 25 students, so they have a list of 25 grades. And they want to put that into some kind of a visual summary. So this case, he creates some class intervals. Everyone between 3 and 9 on their score. 2 people got that. Between 10 and 16, 2 people got that. Between 17 and 23, 8 people got that, etc. If we look at these numbers, 10 minus 3 is 7. 24 minus 17 is 7. You subtract consecutive first numbers, or if you want to, you could subtract consecutive second numbers. That still subtracts to be 7. This is how you find the class width. And then they worked it out. This is, if we divide by 25, 2 over 25 is 0.08, and that's how they're getting the 8%. If you change the size of the class, intervals. So 15 minus 3 is 12. Now if the class width is 12, it makes it look different. So you can decide the size of the class interval, or called bins, and then that makes the picture look differently. Now I went from here and did a histogram. So along the top, on these histograms, we have the class intervals on the bottom, and then the height of the bars corresponds with the percentages, because it's the relative frequency, what percent. So we have between 3 and 9 was 8%, and that bar goes up to 8. Perfect. And so that's the picture if the class width is 7, and if the class width is 12, it's very similar shaped. Some faculty will use this type of analysis to determine grades. A, B, C, D, E, F. And they want to have 6 classes. So they figure out what class width makes 6 classes so that they can have a nice defining A, B, C, D, E, F. E and F, that's weird. They would go 5 classes. A, B, C, D, fail. Okay. Now, if there's a gap in a histogram, that means there's no one in that category. That's important information. So whereas in a bar chart, there's no meaning to gaps, and usually there's gaps between all of them, with a histogram, a gap means that there's no one representing that category. So in this case, how many adults were questioned? So a group of adults were asked how many children they have in their families. Okay? So no children in their families. This is 3, the height. And this is total number of adults, not percent. So this actually represents 3 adults said they have 0 kids in their family. 8 adults said they had 1 child in their family. It's like 5 adults, and this is 2 adults, and this is 2 adults. Looks like 10, 20 adults were questioned. So that's just the sum of the heights of the bars. That's how many adults are represented in this histogram. How many adults had exactly 4 children in their family? This is the bar that's 0 height. No adults answered 4. That gap is meaningful. More than 3, you would add up this one and this one. Now, had it said 3 or more, then we could include the 3 in the category. But more than 3, you couldn't include the 3. So just have to be careful with the English on those. Okay, moving forward. Measures of central tendency. Quantitative data. What's in the middle? The median is the geographic middle of the data set. The mean is when you add them all up and divide by how many there are. That's the typical average people think of. Add them up, divide by 2, or add them up, divide by 3 if there's 3. And then the mode is the most common. You can have one answer for mode. You can have no mode. You can have a bimodal data set. You have multimodal. That's not a unique answer. The other ones are unique answers. All right, so for example, the one on the right. By the way, I don't know how many people we have on here. Did anyone, it looks like there's some people that might not have received these notes. Let me send these notes again. So these are the statistics lecture notes with videos. And then the probability lecture notes with videos. And I also have the cryptography. I don't know if your class is doing the cryptography ones. My class did. The other one will be the normal distribution. I have not made those notes yet because I haven't covered that section. I'm going to do that, I think, this summer and make those. But these lecture notes have basically exactly what we have on the, but they also have a little icon. So if you open those up, you'll see a little icon. And the very top icon actually opens up to study music, if you're interested in. And then the other ones show how do you work the stuff out on the left. So it's blank and I go over the left side. So it's an extra review you can do. But on the right side it says the answer is. And so now I'm doing the work on the right side for you. The mean, you add them all up. And I ran out of room. And divide by how many total there are. 1, 2, 3 times 4, 12. There's 12. And you work it out. So this one is the one that takes the most math. And so you might consider that that's mean, that they make you do all that work. So what we get. Whoa. There we go. The top is 138. And then divide by 12. 11.5. I should just make this bigger, give myself some more room. So the mean is 11.5. The mode is the one that's the most frequent. In this case, it's 20. 20 shows up twice. Now, you wouldn't think the mode is a very good sense of average on this data set. Yeah, in the chat, my tutor helps you remember that your teacher is mean when she averages your grades. Now, that's if it helps, that's good. The issue that I have with that statement is average means 3 different things. So how did she average your grade? Most people average with the mean, so that's why it works to remember that. Now the median. What's right in the middle? What's right in the middle of this data set is a space. To the left of this space, there are 1, 2, 3, 4, 5, 6 numbers. To the right of this space, there are 1, 2, 3, 4, 5, 6 numbers. So if you have an even number of data in a data set, there's a space right in the middle. So if there is a space, then you find the mean of those numbers to the left and right of that gap. 24 over 2 is 12. If there's an odd number, then there's a number right in the middle, and that's the median. Okay. Now, with a frequency table, you still need to find the mean, median, and mode. However, there's a score from 0 to 5. There were 4 zeros and 3 ones. So the frequency table, there were no 2s. There were 2 3s. The frequency table represents a much larger set of data than what you're looking at. So I don't really want to write them down, but on a test, that's a backup plan. Just writing them all down. Instead, I would want to look at, well, there are 4 zeros. So if adding up these numbers, I would get 0. Adding up these numbers, I would get 3. Adding up these numbers, oh, there are 2 3s. I got to erase one of those 3s. What if people were wondering what I was doing? I get 6. So I have to add all these numbers up and divide by how many there are to work out the mean. You can do this by multiplying the frequencies and their scores. 4 times 0, 0. 3 times 1 is 3. 2 times 0, 0. 3 times 2, 6. We're getting the 0, the 3, the 6 out of this. If you multiply them together, you're finding the sum of those numbers. Add all those up, 20, 35, 44. Total 44. And in the denominator, you have to add up the total frequency. 4, 5, 6, 7, 8, 9, 10, 11, 12, and 5 is 17. If you wanted to do this all on your calculator, you need a parenthesis in the top, and it would be 0 times 4 plus 1 times 3 plus 2 times 0 plus 3 times 2 plus 4 times 5 plus 5 times 3, close parenthesis, divide by, open parenthesis, add the numbers on the bottom. 4 plus 3 plus 0 plus 2 plus 5 plus 3. 2.5888, etc. It's 44 divided by 17. Same thing. So that's the mean. We would go 1 decimal place more than the data given. That's a rule that most people haven't heard about. In this class, it's not covered, but I'd go 2.6. So that's the mean. Erase all this stuff so I can see the stuff again. There we go. Hopefully that makes sense. The median. I don't know why it's not asking about the mode. Let's do the mode also. Do that now. Which one's the most frequent? That one, 5. Biggest number. There were 5 4s. The most frequent score was a 4. There were 4 zeros. That's close, but it's not the mode. Now, the median. The way to find the median is basically the median is at the 50th percentile. To find the 50th percentile, we work out 0.5, 50th percentile in decimal form, times how many there are. There were 17. We get 8.5. If you get a decimal, when you work out percentiles, you always round up. Even if it's 8.1, you round up. And you've determined that the 9th number is right in the middle. So would this make sense? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 here, and there's the 9th. And then there's a total of 17. There's 8 more to the right. 8 plus 8 is 16, plus that middle is 17. So when you have an odd number of numbers in your data set, there's a number right in the middle. You need to find it. That's the median. So we did half of 17, got us 8.5. And so we go to the 9th term, and that's the one right in the middle. 8 on the left, 8 on the right. That one's right in the middle. What's the 9th term here? 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9th term happens in there. So we have to count the frequencies. 4 zeros, 3 ones, there's no 2s. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the 9th number. It's 3. The mean, median, mode aren't always the same. They are the same in what's called a normal distribution, which you might have covered in your class. Which one's a better measure of average? That depends on what you're looking at. If you want to know how many, do you have the average number of eyes for a human? Some people don't have an eye because of whatever reason, so the mean number of eyes would be like 1.9 something. No one has the average number of eyes if it's the mean. But the median and mode would both be 2, and so those would be the best ways to ask about that. All right, now, variation. We have the percentiles and the 5-number summary. So again, this is a review of percentiles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 numbers. The 25th percentile, that's a round up. Third number is the 25th percentile. The 50th percentile. Now, if you work a percentile out, and that number is a whole number, this represents that there's a gap, and you need to do the mean. So then this tells you to do the mean of the 5th and the 6th. This is how you do the whole number. So if the percentile is a decimal, you always round up. If the percentile is a whole number, you do the mean of that position, the 5th one, and the next one, the 6th one. 1, 2, 3, 4, 5, and 6 would be 8 and 10. 9. That's how you work out percentiles. Let's do the 40th percentile. 4, 5, 6, 7, 8, 9, 10, 11, 12, 17. Again, there's 17. This is the same data set. Oops, I write a 4. 40th percentile is 6.8. I should not trust my brain on review day. .8, and then round up to the 7th. 1, 2, 3, 4, 5, 6, 7. 40th percentile would be a 1. All right. The percentiles, the Q1, the 25th percentile, is the first quartile. The 75th percentile is the third quartile, and the 50th percentile is actually the second quartile, but most people just call it the median. The 5-number summary is the minimum, first quartile, second quartile or median, third quartile, and maximum. So the easiest one, minimum, maximum. The quartiles, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of them. This would be 2.5, so go to the third. 14. 50th percentile, that would be 5, and so the mean of the 5th and the 6th. For 5 and 6, between 28 and 40, that's 68. Half of that is calculator work, review day. Add them up, divide by 2. 34. 75th percentile. 7.5, round up to the 8th. That's the 56. So the 5-number summary is 1, 14, 34, 56, 69. Not too hard to find. It's all about percentiles. This is the percentile method that's covered in the book. So your test might say find the percentile method by the method, or find the 5-number summary using the percentile method covered in the book. That's what they mean here. Box plots, a visual representation of the 5-number summary. So this is this is the minimum, this is Q1, Q2 or the median, this is Q3, and this is the max. Those the 5-number summaries correspond with the 5 vertical lines. The middle vertical lines, there's a box created around them, and then the others just have a little whisker. These are often called box and whisker plots. They can be vertical as well. And I put this in here specifically for the Magnets of Pain project because the pre-pain levels were these kind of box plots. This is a common question because you can use 2 box plots to compare populations. Would you rather make the 3rd quartile salary for a construction worker, right here, about $46,000, or the 3rd quartile salary for a teacher, $45,000? Well, that's like $46K. Whereas this is only $45K. So if it's just based on numbers, you'd rather be a construction worker. But they have to work summers, so there's more going on there. If you make the 1st quartile salary for a construction worker, 1st quartile salary, $35K, you're making more than what percentage of teachers? Now, each section is 25% because these are quartiles. So this value of teachers is bigger than 50% of the teachers. So the box plots are subdividing 25%, 25%, little 25%. A whole bunch of people are stuck in that range of salary, 25%. There's the 100% of the people. Are there more, less, or equal numbers of workers between Q1 and the median in Q3? Q1 and the median is this number. Median in Q3 is this number. There's equal number of people in these quartiles. Even though the box itself might be really skinny, it still represents 25% of the population. Equal numbers. What percent of teachers make less than the median? Well, half of them. There's always half of the people that are less than average or greater than average if the average is the median. Finally, we get to standard deviation. I think for this case, rather than doing one, I'd rather just cover what to do. And this picture is really nice for that. So here we have 10 numbers. The first step is you find the mean. Add them up, divide by 10. The next step is you subtract the mean from every value of the data set, etc. 77 minus 78.8 is negative 1.8, negative 5.9, 7.4, etc. So that's just subtracting the mean from the original data. If it's negative, that means that the number was less than the mean. If it's positive, the number was greater than the mean. Now we square all those values. We still have a list of 10 different numbers. Now they're all positive. To do the sample standard deviation, which is the only one covered in the course, you find the mean of these 10 numbers, but instead of dividing by 10, we divide by one less than 10. I call this the quasi-mean. The point of this step is the sample statistic, the sample standard deviation, is always smaller than the population standard deviation, just because of how the math works out. So to make the sample standard deviation better represent the population standard deviation, we do this one change. It makes a bigger answer that's closer to the true value of the population. Now this number is the quasi-mean of all the squared numbers, so it's too big. Then we square root it, and what we end up with is called the standard deviation. Going by hand, you don't want to do too many of those. So the example that I have for you to do would be 5. Just 5 numbers. So you add them up, divide by 5, subtract that from each one, square those numbers, then add those up and divide by 4, and then square root. Okay, so a lot covered there. Now, I think the next thing we should do is the probability, but I might want to speed up a little bit and ask you what you'd like to look at, just for time's sake. I'm fine going to 11 o'clock, but I think that's what was in the, let's see, where's that? There. No. There. No. What did it say? It just said starts at 9 a.m. There's no ending time. Okay, fine. So here we have the probability. The probabilities are proportions. The basic definition of a probability is this: the number of outcomes corresponding to the event you're interested in divided by the total number of equally likely outcomes. As far as typical experiments that happen, flipping a coin, there's just heads and tails. Rolling a 6-sided die, 1, 2, 3, 4, 5, 6. If it says a standard die or standard dice, you assume it's 6-sided. So no Dungeons and Dragons rolls here. A standard deck would include 52 cards, the American standard, and there are 4 suits, hearts, diamonds, spades, and clubs, and there are 13 cards of each suit. Ace, 2, 3, 4, up to 10, Jack, Queen, and King. If you are English language, second language learner, some of this might be like, I had no idea about standard cards in America, so they should have that in the problem. Hopefully they do. Okay, so what's the probability of rolling a 3? Well, there's exactly 1 3. Oops. Let me get at that. Come on, draw. There we go. I just had to get my drawing tool. There we go. So there's 1 3, and there's 6 total. That's that. Probability is easy to do. How many even numbers? Well, there's 3 even numbers on the 6-sided die, and 6 total. That can be reduced. A 4 or a more, you can get a 4 or a 5 or a 6. So again, there's 3 out of the 6 total. Probability is 1/2. From a standard deck, how many are not queens? Well, there's 13 total in a suit. 1 queen. So there's 12 of each type. There's 12 hearts, 12 diamonds, 12 spades, 12 clubs that are not queen. So we can do 12 out of the 13, or we can do 48 out of the 52 if we want to add up all the cards. There's 52 total cards. There's 48 that are not queens. But you can also say there's 13 in a suit, and 12 of those are not queens. These are the same numbers. This would all be fine. Jack of diamonds, so this is Jack and diamonds. There is one Jack of diamonds out of the 52. If it said like Jack of pluses, there's no pluses in a deck of cards, so that would be 0. That's a silly one, but some of the other questions are like that. Okay. Here we have a bag of M&Ms. 6 red, 3 green, 4 blue, 8 yellow. What's the probability of randomly picking a yellow? How many yellows are there? There's 8 yellows. How many total are there? 21. We have to figure out how many total there are so we know what to divide by. What's the probability of picking an orange? There are no oranges. That's called an impossibility. When you work out probability and the answer is 0, it's impossible. Okay, the probability is always between 0 and 1, or if you're looking at percentages, 0% and 100%. Sometimes people like to look at probability in percentages. Okay, multiple events. We have the complement. That's like the probability of not a queen. If you roll a 6-sided die, what's the probability that is not a 5? So if we look at the sample space, these are all the different things that can happen. And so if we wanted to count how many are not 5, we get 5 of them. So we can directly count how many are not a 5. But we can also count how many are a 5 and do the probability of 5 is 1 minus the probability of not 5. Let me do it the other way around. The probability of not 5. Probability of 5 not 5 is 1 minus the probability of 5. 1 minus 1/5, which again is, 1/6. 1 minus 1/6. Which is 5/6. So you can do the not 5 in 2 ways. You can add all the ones that are not 5, or you can just add the one that is a 5 and do 1 minus that. So 1 minus is pretty easy math, although it is fractions. So do you want to count 1 or many? That's really your choice. Independent events. Having children are independent events. If you get a boy for your first child, chances are still equally likely you'll get a boy or a girl for the second child, statistically speaking. Actually, I think based on numbers, it's slightly higher chance of getting a girl than a boy, historically. But we assume they're equal. So if the events are independent, whatever happens on the first one has no bearing on whether it'll happen again, then you can do the AND probabilities with simple multiplication. A jar contains 12 red marbles, numbered 1 to 12, and 6 blue marbles, numbered 1 to 16. A marble is drawn at random, its color noted, and replaced to the jar. This is repeated for the second marble. Find the probability that the first marble is blue and the second is even. So the probability of blue and even. Now, because we put the first marble back in, the probability of the second one being even is the same as if it were the first one. So these are independent events, so we can do the probability of blue times the probability of even. Okay, how many blue ones are there? 6 out of how many total? 12 and 6 is 18. Times an even one. Half of them are going to be even. And then we can reduce this. See, 9 goes into 18 twice. 2 goes into 6 3 times. 3 goes into 18 6. Oh, 1/6. It all ends up being 1/6. And you'll want to also make sure you know how to do this kind of stuff on your calculator. This calculator, for example, has a button that converts to fractions. Have a nice backup plan with fractions on your calculator. Know how to use your calculator well. The with and without replacement. If we choose two M&Ms with replacement, we want to choose a red one and then a green one. Well, the first time we go in, 6, 9, 10, 13, and 8 is 21. So again, there's 21 marbles here. M&Ms. And we put them back in. I like to do these with marbles because you're not going to eat a marble. And if someone else touches those marbles, who cares? Wash your hands. Versus someone else touching your M&Ms and putting them back in, you're like, I don't know if I want to do this game anymore. But in this case, you put them back in. Red, there are 6 out of 21. Times, and is a multiplication process with probabilities. Getting a green one, well, there are 3 greens out of the 21. So because we put that red one back in, there's still 21 in the bag. That's why our denominator is still 21. This is different if it's without replacement. If you eat it, or just don't put that M&M back. We get the red one. There's still 6 reds out of 21, but we eat the red one. What's the probability of a green one? There are still 3 greens, but now there's only 20 M&Ms in the bag because you kept the first one. Now, if this had been the probability of red and red without replacement, then it'd be 6 out of 21, and then there's only 5 reds and 20 total, etc. So you just have to pay attention that when you do it without replacement, there's a fewer number in there. That's a look at the new situation and then determine what the probability is. Now, the OR probabilities. Probability of A or B is defined as the probability of A plus the probability of B minus the probability of A and B. Okay. I'm wondering if I have... Where did I find that quick? There we go. Let me just drag this in. So this is the sample space of a deck of cards. It's all the possible cards in there. And we want to know the probability of ace or hearts. So there's a combined total of 4 aces. And there's a combined total of 13 hearts. But if we add up 4 plus 13, we will have double counted that ace of hearts. So 4 plus 13 is 17. But there are not 17 aces or hearts in here. There's only 16. The 12 hearts that are not aces plus the 4 aces, 16 cards we could win. So if we were randomly selecting and we'd win, if we got an ace or hearts, there's 16 ways we could win. You can't count that ace of hearts twice because it's only one card. So the way we can do this with probability is find the probability of aces, 4 out of 52, plus the probability of hearts, 13 out of 52, minus the probability of ace of hearts, 1 out of 52. And that way we can get rid of the double counting. So this would be the probability of ace plus the probability of hearts minus the probability of ace of hearts, the and. Aces, 4 out of 52. Hearts, 13 out of 52. Ace of hearts, 1 out of 52. And we have 16 out of 52, which then you would reduce. 8, 4 out of 13. I think it's 4 out of 13. But that kind of stuff you check on your calculator, especially on test day. Don't mess around. There it is, 4/13. So this is the OR rule. So the AND rule, you multiply probabilities. Since probabilities are less than 1, when you multiply them together, they get smaller and smaller and smaller. It's harder and harder to meet the AND conditions. And so the probability gets smaller that that's possible. The OR probability is an addition, meaning A or B is easier than A and B. And so the probability should be larger. That happens when you add probabilities together. Okay. The probability of at least 1. So basically, at least 1 is 1 minus the probability of none. This is the complement rule. An experienced teacher writes an exam so that on average about 5% of students will earn an A. I don't know why the experience part in there is. If you're really that experienced, hopefully you have more than 5% of your students getting an A. This might be more like an inexperienced teacher. Okay, but regardless, 5% of the students will earn an A. If she has 50 students, what's the probability that at least one student gets an A? Okay, so the probability of at least one A in 50 tries, because remember, we're doing some kind of random selection here. They have all the names of the students in a hat, and you pull that number or that piece of paper out, and on the back side of their student number has their letter grade. And so you randomly select one, you take a look at it, and then you put it back in. And then you randomly select one, you look at it, put it back in. You do that 50 times. What's the probability you'll get at least one A? So this is equal to 1 minus the probability of no A's 50 times in a row. It's not likely. So no A's 50 times in a row is no A, and the next one, no A, and the next one, no A, and. So this 50 times in a row is a series of and probabilities. And probabilities you multiply. So this would be 1 minus the probability of not A to the 50th power, because they're going to be multiplied together, 50 of them. Okay, so probability of getting an A is 5%. The probability of not getting an A, therefore, would be 95%. The other 95% of people don't get an A. We have to find one of those 50 times in a row. 1 minus 0.95 to the 50th. 92.3%. Accurate to 3 decimal places. They don't say percent, so we don't go to percents. 0.923. There's your approximation. The probability of getting at least 1 is 0.923. Thought of in percents, 92.3% of the time you'll find at least one A out of those 50 students. The at least one rule. Okay, we now get into two-way tables. The two-way tables are either given, or if it's an incidence rate problem, you have to create it yourself. The probability of out of state. Now the total column is very convenient. There are 27 that are out of state, out of a grand total of 65. So they've already done subtotaling and grand totaling for you on these. The probability of getting a C, subtotal 20, grand total 65. And all of these you would simplify, if possible. Use your calculator, if necessary. I know 20 out of 65 will reduce because there's a 5 that I can pull out of both of them. So that would reduce to 4 over 13, as an example. 27 65ths does not reduce. Probability of not A. Now for the not A, we can look at all the ones that are not A. There they are. We have subtotals. There are 58 that are not A's. We can just add them up directly. Or we could do 1 minus the probability that they are an A with the complement rule, and also get 58 out of 65. So we have a rule for that, but the two-way tables with their subtotaling already just makes it easy to just add them up directly. How many are not A's? 38 plus 20, 58 out of the grand total. In state and a B. There they are. Those 20 people are in state and B's. This next one is interesting. Out of state or A's. This time I don't go to the subtotals. Because if I do the subtotals, then I will have some double counting problems. If I looked at the out of state or A's, the 27 and the 7 include these. The 27 include these. You can see the 4 people that are out of state A's are double counted. I don't want to mess around with that. So for the OR problems, I don't use the subtotals. The way I do it, I feel is safer, is just circle each of them that are out of state or A's. There are 4 things circled. The A's, 3 and the 4, don't go to the subtotals. And the out of states, the 4 is already circled, don't do it twice. The 18 and the 5. And add them up. 3 plus 4 plus 18 plus 5. 30. 30 out of 65. I think that's safer. You know you're not double counting because you didn't circle that 4 twice. The other option would have been the 7 plus the out-of-state 27 minus the double counting. You'd have to subtract the 4 to get the right answer. And that's with the OR rule. Probability of A or out of state is the probability of out of state plus the probability of A minus the probability of out of state and A. The rule works, you just have to remember to use it. I think it's safer just to circle the individual numbers. All right, moving on. Conditional probability. There's a rule that I don't typically use. I know how to use it, fine, but I don't need to use it. It's the probability of A and B is equal to the probability of A times the probability of B, given that A has already happened. And that's exactly what happened prior. Let me go up to the marble problem. There it is. Probability of red and green is the probability of red times the probability of green, given that red already happened. That's the 6/21 is the probability of red. And the probability of green, given that red has already happened, is 3/20. So we've actually already experienced this rule without replacement. Okay, so how do we do it? Essentially, what I consider on these, I think it's a little bit easier way to consider it, is this second part, given that A has happened, probability of in-state, given that they have an A, tells us that we're stuck in this column. We're stuck in the A column because we're given that A happened. So we're only looking at those numbers for this conditional probability. What's the probability of in-state? 3 at a grand total 7. We don't look at the overall grand total of 65 because we're not in that population. The given stuff, given an A, tells us which population we're actually in. So just limit yourself to that row or column, depending on the situation, and then these are basic probabilities. Like this next one, probability, oh, my eraser just stopped erasing. Probability of A given in state. So this in state tells us that we're stuck in that row. Don't look at any numbers outside of that row, and you'll be good to go for this. Find the probability that you got an A. In that row, there are 3 A's out of the total of 38. Conditional probabilities are almost trivial when you have the two-way tables. Next one, probability that you're male, that you got a C, so you're stuck here. You're got a C, males, 9 out of 23. That's different from what's the probability of getting a C if you're male. Now, you're male, you're stuck here. Probability you got a C, 9 out of 24. It's a little bit different. You cannot reverse the order of the conditional probabilities because they're different values. Okay. So we have the incidence rate creating the two-way tables. And some people have tried to remember Bayes' theorem to do that instead. Bayes' theorem works, but it's not formula that's given, so you have to memorize it and understand how to use it. And so I think the two-way table method is a little more straightforward. And we still have expected value left in probability. Okay. So a certain disease has an incidence rate of 2%. I start these out by picking a sample population. I like to work with 100,000. But if the problem says 1 in 400, then I pick something 400 and add a couple zeros to that. Then I would work with 400,000, just to avoid decimals or fractions here. So if I pick 100,000, the incidence rate for this disease is 2%. 2% of 100,000 is 2,000. There are 2,000 people infected in this population. So again, this is 2% of 100,000. 2,000 people. That's the incidence rate. Now the other 98,000 people must not have been infected. We have a total of 100,000 people. So we now have the totals of the people worked out. All right. Next up is this false negative rate. False negative are the ones that are not infected. No, wait, false negative. It's negative and it's false. It's this one. That's false negative. Why is it negative? Well, it's in the negative column. Why is it false? Because they were infected. They should not have gotten a negative test. So these 2,000 people, 10% of them got the wrong test score. 200 people. So 200 out of 2,000 represents 10%. 10% of them got a false negative. They should not have gotten a negative. The other 1,800 people, that's 2,000 minus 200, got a true positive test. They're infected, they got a positive test. That's what it should have done. Now the false positive rate, it's positive and it's false. They were not infected and they got a positive test result. That's false. So the 98,000 people that were not infected, 1% of them got a positive test result. 980 people got a false positive. The rest of them, I got to work that out, got a true negative test result. 97,020. They got a true negative test result. So now, to find the totals, add them up. We have our two-way tables filled out. To double check that we did this right, add up the bottom columns, 2780, the subtotals. Make sure that that adds up to 100,000. Excellent. It all matches. So now that we have the two-way table, now we can do the probability that a person who tests positive, so that's given positive, actually has the disease, infected. We want to find the probability that they're infected, given that they tested positive. So, who tests positive forces us into this column. Probability that they have the disease, well, there are 1,800 people out of the 2780 total. 0.647. Oops. Approximation. So they tested positive. Only 65% of the people that test positive actually have the disease. And this is with a very low 1% false positive rate. A lot of tests have a higher percent rate than that for false positives. But we determined 64%, 64.5% of the people that get a positive test result were actually infected. The rest of them were not. This is the type of mathematical argument that the courts have used to basically not accept lie detector tests for proof. Because even if they're lying, the test might still say they're not lying. Or even if they're not lying, the test might still say they're lying. They're not infallible. They have all these false positive, false negative rates. And the numbers are just too significant. I mean, 65%. That's 35% of the people that got a positive test were not infected. That's too bad a numbers to justify any kind of punishment. All right, finally, expected value. There's two situations you find yourselves in. One is where it costs money to participate, like to buy a raffle ticket or to buy insurance. And the other one is if you're just playing a game and you're wondering what's the chances of certain things happening. It doesn't cost money to participate. So I like to do the stuff that costs money a certain way. The books don't show it much, but I think it's just so much easier. So in this case, tickets for a raffle cost $19. There were 719 tickets sold. One ticket randomly selected, the person wins $1,500 and given their ticket cost back. For someone who buys a ticket, what is the expected value? So what this would look like is the value of buying a ticket to the person is losing $19. Let's assume that happens every time. This is the way I gamble. I assume I'm going to lose the money that it costs to play the game. Just like if it was playing a video game. Money's gone. Now I'm just going to enjoy myself. Might make money, might not. So, guaranteed losing $19. Now there happens to be a chance, a 1 out of 719 chance, that I earn $1,500 plus my ticket money back. So I would earn $1,519. So I'm guaranteeing to lose $19 with analyzing it this way. Just that money's gone. And there's a chance that I earn $1,519. You just work it out, see what you get. Negative 19 plus 1519 divided by 719. Negative 1689. So I'm expecting to lose $16.89 per ticket. This is silly to me. I'm buying a raffle. I expect to lose $19. But the people that are giving the raffle tickets, that they're selling them for this prize, they expect to make $16.89 per ticket because they're going to be doing lots of numbers. 719 tickets sold total. So as an individual, yeah, you can say you expect to lose that much money, but that's not really important unless you plan on buying a bunch of tickets. I'd expect to lose it all. It's a raffle. It's a donation, basically. That way I'm never disappointed, and sometimes I'm really happy. If it doesn't cost money, the outcomes are easier to identify. So in this case, kid in North playing a game, one card at random from a standard deck. Kid selects a face card. North pays him $4. If kid selects any other card, he pays North $5. What is North's expected value? All right, so to North. North pays $4, so minus 4. The probability of that happening is if kid selects Jack, Queen, or King. There's 4, 8, 12. There's 12 out of 52 cards that are Jacks, Queens, or Kings. And in those cases, he loses $4. North does. But he gains $5 the rest of the time. That's 40 out of 52. I just did 52 minus 12. Got 40. Those are the other types of cards. And you work it out. See what you get. $2.92. North expects to make $2.92 every time kid selects a card. Definitely want to play that game if I'm North. Okay. Another example with just basically the same stuff though. Okay. Hour 26, 10:44. The next question I have is, do you want to see, I think most of the students here are from my class, and so my feeling is that I should do the cryptography next, and then after that look at the normal distribution. I think that'll help the most people that are here. All right, so let's open those up. Out of the way for a second. Get the drawing window open. There we go. Okay. Cryptography. Secret codes. We have the substitution ciphers. These are really easy because they just tell you how the substitution is. But then we also have the Caesar shift ciphers. So you might or might not have the alphabet to work with here. Decrypt the word if it was encrypted using an alphabetic Caesar shift cipher with shift 17, mapping A to R. So if you don't have anything to work with, your job first off is write the alphabet. Then A is mapping to R, so we start below A with an R and write the alphabet. When you get to Z, start over. The next one should be the R. There we go. So the encryption goes down, the decryption goes up. So we're decrypting N, so we find the N, gives us a W. Then the Y gives us an H. Then the F gives us an O. And the C gives us an L. And the V gives us an E. We've decrypted this word using a Caesar shift cipher with shift 17. Now, if you didn't have the shift 17 mapping A to R, you could just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 is an R. Now you know A goes to R. So the shift of 17, just move 17 down the alphabet, and that's how you know what number is mapped to A. Not too bad. You might also have a random cipher like this. Paper. You just go to P, this is J. Go to A, it's a Y. P is a J. E is an M. And R is a T. Going down, encryption. Going up, decryption. The only main issue I see with students here is encrypting an encrypted word. So re-encrypting it. Then it gets, it just doesn't help. Now, question, do you have the circle Caesar shift wheel on the test? No. So it'll just be a question like this one on the right. I do believe that I wrote the alphabet for you, so you only have to write the new shift underneath it. Okay, repetitive Caesar shift. I really don't want to write the alphabet again. So let me go back and use the previous one. Since the alphabet's written. Oh, I didn't mean to undo all that. Well, you've got the notes, so sorry, I didn't mean to do that, though. A is mapping to B. So it's just a one shift over. So G will map back to F. Now with a repetitive shift, so in this case, since it's only a shift of 1, to decrypt we have to go backwards 1. So that's G is going back to F. But it's a repetitive shift. So to go for the next one, N, I have to go back 2. I have to go back 1 more than I did before. So the N would go back, 2. L. And the R would go back 3. And O. And the S would go back 4. And O. And the W would go back 5. R. So you can use the alphabet to decrypt and encrypt when it's a repetitive Caesar shift. If it's an encrypting by going forward 18, the first number go forward 18, the next number go forward 19, the next letter, go forward 20, etc. And going backwards, the first one go back 1, the second one go back 2, or the first one, if it's a forward shift by 10, then the first letter go back 10, the next one go back 11, the next one go back 12. And you could do that efficiently with just a list of number or letters like the alphabet here. Repetitive. Okay. Tabular transcription cipher. Encrypt the message at noon, spy on headquarters using a tabular transcription cipher with rows of length 6. Let's see, 1, 2, 3, 4, 5, 6. It doesn't really matter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 23 letters. So we need to go 4 down. So it would be at 1, 2, 3, 4, 5, 6. These are the columns. 6 across. And it'll go 4 down. Spy on headquarters and pad the message with A's at the end. Now, if there's no keyword, we just list the coded message going down the columns. ASERTPATNYDE 0OOQR ONUS NHAA. You don't have to have spaces in between there, you just send that message. Without a keyword, they usually do have the spaces, like on the left. Otherwise, you don't know to make it 4 down when you're putting it back together. This one says rows of length 5. How many are there? 1, 2, 4, 8, 12, 16, 20, 24, 28, 30. There are 30 total, and it's 5 across, then it has to be 6 down. Here's our table. 6 times 5 is 30. This has space for all 30 letters. And now we just start putting them back in. But these were given, and we put them in vertically. Or the ASIH AARW DTCDTS. So that's the tabular transcription, and then we read left to right at midnight. Lots of bad letters in there. And then we can, oops, not at, it's attack, headquarters, and a little WS filler at the end. So that we can get our message out of that. At midnight, attack headquarters. With all the examples being headquarters and attack and spy and everything, clearly this coding was primarily a war conversation. Caesar, Shift Caesar being involved in lots of war campaigns. Keywords. You have to know the keyword. Basically, it's still the tabular transcription. Let me write the word write. This is the keyword. First off, that defines the size of the table. And so now we write it at 9 head south to trenches. No filler words needed here. The next thing you do with the keyword is notice the alphabetical order of the letters in the keyword. The first letter of write in alphabetical order is E. That's the last column. So then you give that column first. The next one is the I, then the R, then the T, finally the W. That also gives you the order to give the code. So this would be NDHES, NEUTH, THOOC, IATRE, AESTN. They would get this message, they would need the keyword. Without the keyword, computers would be able to break this in about 2 seconds with or without the keyword. That's why we have the RSA encryption nowadays. But back in the day when you didn't have computers, you just have to, I don't know the size. If you don't know the keyword, you don't know the orders. There's a lot of variability here to figure out what it is. And if you do the Caesar shift to begin with and then code it, then you have to know the Caesar shift decoding and then put it into the table. And you can definitely make your own method that's not easy to break unless someone's a code breaker and have a computer and they can still run analysis. Okay, here we have encryption keyword was Oregon. So that gives us the size of the table. Now this is an interesting one because it's Oregon. There's 2 O's. By the time we get there, hopefully we can determine which order goes based on the wording that's showing up. We can know which one should go next. I'll go alphabetical order as a first guess. Don't know how long these have to be. But this is the first one. E is the first in the alphabetical order. Then G. And then the O's. But we know this will be 3 or 4. This will be the 5th one. This will be the 6th one. So the only orders I'm not sure are the Oregon. So we start off with, let's see, 3, 6, 9, 12, 15, 18, 21, 24, 27. There are 30. So this is going to go down 5. 1, 2, 3, 4, 5. It's 6 across. It'll be 5 down. All right. So let's fill out this one. O, V, N, M, N. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just to, because I'm going to have to put them in different orders. The second one, N, E, C, oops, C, E, P. I don't know about the 3rd and 4th. Let's do the 5th one next. E, I, E, M, V. And the 6th one, T, R. Oh, wait. I had in the wrong spot. A, E, A. And now, I'm going to guess the O's. So we've done, we're looking at this one and this one. Would it make sense to, we can try it. If this were S, L, O, Y, Z, Y, E, M, E, E, Y, E, M, E, I, maybe, I, O, A, right there, I, O, A, N, that does not seem right. Too many vowels in a row. So I would guess it's the other one, A, U, L, N, C. This is only 50-50 chance. It's pretty safe to try one and take a look at it, and if it doesn't work, swap it. Too many vowels in a row. Let's see. At, shouldn't that be an E? I think I've got these reversed. I don't know what I've done. Oh, N becomes before O. Was anyone going to clue me in? I had the alphabet wrong. Oh, Celeste, thank you. N before O. Duh. Oh, that's sad. All right. Well, yeah, that's something was off. It was looking good, but it didn't sound right. I don't know my alphabet. Well, that would definitely put a damper on coding if you don't know your alphabet. All right, so that would be the E. E, I, E, M, V. And S, L, O, Y, Z. At one, surveil. There we go. At one, surveillance on enemy camp. Whew. That was a crazy code. Celeste, thank you for saving me. So the keyword, the O's were the only issue, other than I couldn't do the alphabet well. And it was this one. First, second, third. The fourth and fifth were the questions. And so it was in alphabetical order, the fourth and then the fifth. So it was just the first O goes here, the second O goes here. So that was good. Alphabetical order. All right. Modular arithmetic. This starts the basis of our modern encryption methods. 34 mod 5. If you go 5 into 34, you get 6. 6 times 5 is 30. Remainder 4. The answer is the remainder. That's how we do modular arithmetic. And very quickly you realize that you can just do a calculator. 34 divided by 5. There's 6 is this 6 here. We subtract that because we're only interested in the remainder. So we subtract the whole number part. And 0.8, if we multiply the 5 again, gives us our remainder. So we see that there's a calculator approach. It's divide, subtract, multiply. So 75, divide by 4, subtract the whole number part, multiply by 4. 3. $25.43. Divide by 6, subtract the whole number part, and multiply by 6. 5. So what we're looking at is the remainder. We're doing our calculator just because of how easy it is. But 6 goes into 25.43 if you had to. This is 4. 24, subtract 1, 14, 2. 12, subtract 2, 3, 5. 30. That didn't go 30 times 3. 18. There we go. Subtract 5. Remainder 5. 5 is the answer. It's just a long division, but doing it with our calculator for these larger numbers that are involved. So like this one, 5, 3, 4, 6, 4, 3. Divide by 465. Subtract the whole number part. And multiply by 465. And we get the mod. modulus 358. Now the modular exponentiation rule. The mod n, basically we're replacing the a to the b with a mod n to the b. That's the change. So we're replacing this with 45283 mod 11 to the fourth. This is the modular exponentiation rule. This is what you use when the number is just too big to work with. It's a number to an exponent, mod something. That number, you can modulate it as well. Modulus 11 makes it smaller. It's actually even better to see that pattern. Let's show you that whole pattern. There we go. The exponent and the mod don't change. You're just taking this number and making it smaller by looking at its modular number. Now, why this is important is if I looked at 45283 and raised it to the fourth power, it's big. If I divide by 11, I can't subtract the whole number part from that. It's too big. So instead, we make the 45283 number smaller by doing its modular 11. Divide by 11, subtract whole number part, multiply by 11, is 7. So we can convert this number to 7 to the fourth, mod 11. And now it's something we can do on our calculator. You won't have the online tool some people use for this on the test, so you need to be able to do this rule. 7 to the fourth, 2401, mod 11. Divide by 11, subtract whole number part, multiply by 11, 3. There's no other way to do this problem with your calculators, scientific calculators. It's too big of numbers. All right, now we get to the final thing. There's public key transcription or cryptography. This is the Diffie-Hellman-Merkle key exchange. Basically, Alice and Bob start by giving a certain set of generator and prime modulus, and these numbers have to be really well thought out. This is not an easy thing to start with, but there's lists of things you can start with. And then each person picks their own secret code, their secret number. Alice picks 8, Bob picks 6. You can pick whatever you want. And then you mix your stuff, your secret number, with the shared numbers, and you come up with a number, 16 for Alice. And Bob uses 6, and he comes with 15. And then you give that to the other person. And then they work out with that number, combining with their secret code, and they end up with a 1. Bob does it with his secret code. He gets a 1. That's how they get their shared secret key. This would then form the basis of another encryption method. So this is just to get a shared key for another encryption method. Versus the RSA is actually a way to encrypt. Now on the formula sheet that you'll get on the final, hopefully they give that one to you, you have this G to the n mod p. G P, and the secret number is the N. And the G starts at 3, but then it changes to whatever you're giving them, or whatever they're giving you. So here we have an example. Doing a Diffie-Hellman-Merkle key exchange with Adrian using generator 2, so that's G, and prime number 37, that's P. Your secret number, that's N. What value do you send to Adrian? G to the N mod P. This is 2 to the 10 mod 37. And this isn't that big, 2 to the 10. Mod 37. So divide by 37. Subtract whole number part. Multiply by 37. 25. That would be the number, that you would send on to Adrian. He would then combine that with his secret number, which we don't know, and come up with your shared key that would be the same. He still has to send you his secret, his exchange value. We don't know what it is. So now here we have example 30, where you're doing an exchange with Paulina with, again, generator 2. This time it's prime 29. And you've got your secret number. You have no idea what Paulina's secret number is, but she sends you an exchange value of 2. So your G to the N mod P in reverse, you don't use the G. You use the exchange value. So we would do 2 to our secret number, mod 29. So it's either you start with the G, the shared generator, or you use the exchange value they send to you for the base. Then you work the modulus, and you end up with 9. And now Paulina, you're going to share your exchange value with her. She already did her work and sent you 10. No, she sent you, what she sent you? Send you 2. You would do your work and send your exchange value to her. She would combine her exchange value with her secret number, and she would get 9 as well. And so even though you don't know her shared number, you guys both ended up with the correct shared key. It's secret. So it's G to the N mod P for going forwards, and exchange value to the N mod P going back. These are the exchange to them, and what's the secret shared key. These are your formulas. And this is all just to get a shared key that you would then use as the basis of encryption. This isn't an encryption method. This is just to get a shared key. It's like the spark for the encryption method. RSA shared key encryption decryption. So this is a little different. But it's still based off of the G to the N mod P concept. But in this case, it's the N is the P value. It's kind of weird. The E is the N value. Crap, how do we do this? So this is the encryption. It's the exponent and it's the encryption. You'd think of the E as the exponent, but you would also think the E is the encryption. And the number you want to encrypt, so the message, is the base. So the message to the E mod n is how you would encrypt it. So in this case, it would be the message 6 to the E7 mod 33, and you just work that out. Divide by 33, subtract the whole number, multiply by 33, 30. So our number 6 would be encoded as 30. We would send Alice 30, and she would know her decryption code. She was the one that worked out her decryption, encryption, and combination. And she shares the 33 in the encryption 7. We don't know her decryption number. But then we send her 30, and she uses her decryption to get the original message 6 back out. Now we're Alice. And somebody sent her the number 2. She wants to decrypt it. So it's the message decrypt. So the message is always the base. And E for exponent for encrypt, to encrypt something, and a D to decrypt something. And then the other number and the shared stuff is the mod whatever. So in this case, the decryption number, we want to decrypt 2. The decrypt key is 3, mod 33. And now that's just 8 mod 33. 33 doesn't go into 8. 8 is the remainder. So the modulus doesn't change the number until it's bigger than that 33. So 34 mod 33 would be 1. 33 mod 33 would be 0. But anything below that is just the number. And if you really tried that with your calculator, if you're like robot mode and on a test, sometimes that happens. 8 divided by 33. Subtract whole number part. No whole number part. Times by 33. Hey, the answer is 8. Modulus doesn't do anything to a number less than the modulus number. The last piece of the puzzle is the ASCII codes. Basically, all the letters. The ASCII code is well known. It's the same everywhere. Letters are given a number. So are punctuations. So are emojis. Everything's given a certain number in the ASCII world. And so you take a number like joy, a word like joy, and look up the numbers that joy is, like J is 74, O is 79, etc. And then you take those numbers and you would encrypt them with like RSA. Message encrypted mod n. You get these numbers. And then you could send that to the person who gave you the RSA public key stuff. They would know their decryption. They know their D, whatever it is. And they could decrypt this to get back to these numbers that they can look up in the code and see, oh, they sent me joy. Isn't that nice? All right, so that completes the cryptography module. It looks like we only have 3 people on the call now, and I think I recognize all the names, so you are all in my class, so there's no point in going into the other other module that we didn't cover, the normal distribution. So, are there any questions? Yep. Long numbers without the calculator. Let's see if we can do one of these without the calculator. The one I put on the test, the numbers are small enough you can do it. But if we have like 89 to the 5th, oh, it's big. And you might have scientific notation on your calculator. But when we divide by 2021, you should be able to see those 7 digits of whole number part on your calculator. You subtract that, and then multiply by the 2021, and you'll get that 71. Rounding error, but you see how hard it's trying to be 71? Give it the benefit of the doubt. Does that make sense? So the next question is, what formulas are you going to be given? You said what codes? I assume you mean formulas. Okay. I could encrypt the formulas. That'd be evil. Oh no. Oh, that'd be horrible. No, I would never do that. Actually, I would for a extra credit project. Let's see if you're paying attention. So I need to pull up. Actually, I think I need to pull up the actual exam. Exam 3. And now I need to pause the share. Make sure it doesn't pop up on the recording, because that would really suck. And it did. Okay, resume share. These are the formulas you get. So you have the probability formulas, the expected value, and the given probability. Not a lot. You don't have the or the and probability, so you'd want to definitely remember that. Yeah, Lisa, I'll do that next. The normal distribution formulas you don't need. Here's the cryptography formulas. So we have G to the N mod P, M to the E mod N, S for the message that you need to decrypt to the D mod N. So these are for the RSA. Take the message, encrypt it. Take the SPY, I don't know what the S stands for, and decrypt it. And G to the N mod P, the other one that's not given, is the exchange value, EV to the N mod P. So you want to know that as well. The modular exponentiation rule is the one that is being requested one more time. And that's fine. And then the modular exponent power rule, I actually don't use, even though it's the basis of both encryption methods. It's not something you need to know how to do to answer the questions. Okay, so if we had like 3475 to the 5th mod 28, the issue we have in doing this problem is we tried 3475 to the 5th. It's just too big. We divide by 28. It's too big. So instead, we replace this. Oops. Oh, crap. Showed the participants. We replace this with a 3475 mod 28. So we apply the mod 28 to the base that's to the exponent. 3475 divide by 28. Subtract the whole number. Multiply by 28. It's 3. So we change this problem to 3 to the 5th mod 28. So we're able to change the 3475 by applying the mod 28 to it down to 3. We still have the exponent and we still have the mod to work out. But now we have 3 to the 5th. Much smaller. Divide by 28. Subtract the whole number. Times by 28. 19. There we go. Hopefully you were able to follow along with that. Not too many balloon distractions. Okay, any other questions? Yes, you are welcome. And this recording, other than the first page of the statistics, will be available soon, I hope. I'm guessing maybe 2 hours. Maybe a little bit faster for it to process the video. Maybe a lot faster, actually. And there was one spot where it shared the participant, so your names popped up for a moment. But I don't think that, unless you guys want me to edit the video and try to block that out, I don't think it matters. No one said anything. It's just your names. I don't think it's going to be an issue. If someone has a problem, text me now. If not, then I'm okay. All right, good. It was like really briefly, and someone was like, ooh, I can find out who's on this video from somewhere sometime. I guess they can, but I don't think it matters. Okay. Well, at this point in time, it's a 2 hour, 12-minute video. This is quite the review. I think you are on the most wanted list at your house. Man, they're begging for your attention. All right, excellent. Well, I hope you all have a wonderful day and good luck on your exams. Okay, I'm going to end the call. Thank you.